Welcome friends. So let us continue our discussion on Laplace transform. Previously we have solved some problems on Laplace transform, that is to demonstrate the initial value theorem and final value theorem, and also we have accustomed with inverse Laplace transform to get the time domain function from the frequency domain function. Okay. Now in this session we shall mainly study some fundamental signals on which we shall apply Laplace transform. So we shall see what will be the Laplace transform of those signals. So let us consider figure 17 first. Let us consider figure 17 first. We have a staircase like function, so we need to evaluate the Laplace transform of this function. Okay, now to understand this staircase like waveform, we should represent this function in this way. Okay, let us say we have three different distinct time zones t, and in the y-axis we have ft. So you see the first, it is starting from 5 to 10, we have first time zone, then from 10 to 15 we have another time zone, and then 15 to 20 we have another time zone. Let us consider these three distinct time zone. Okay, so from 5 to 10, let us mark that function is like this. Okay, it's 5 to 10, let us say this is function is like this and its magnitude is 1. So if I represent this function as by f1t, okay, then f1t is nothing but u t minus 5 minus u t minus 10. So it is nothing but a gate function. It is nothing but a gate function, right? So what is gate function we have discussed. Now if we consider the second time zone, okay, so which is actually from 10 to 15. So from 10 to 15, so if you consider this as the function, again it is a gate function, but this time we have a magnitude 2. So then if we consider this is as f2t, then f2t should be written as nothing but u t minus 10 minus u t minus 15, but this time we have, since we have a magnitude 2, we must multiply this with 2, right? It is again another gate function, okay, but slightly higher magnitude. It is the double magnitude. Okay, similarly if we have considered the third zone, it is from 15 to 20. So we have another gate function something like that. And if so, this magnitude is 3. So if it is f3t, then similarly in similar manner f3t can be written as, it is 3 times u t minus 15 minus u t minus 20. So now if you add f1t, f2t, f3t, you should get a picture, or you should get a waveform like this. It is a staircase like waveform, you should observe. So now if you consider the first part, that is f1t, now it is simply ut minus 5. So it is simply, actually it is shifted in the time domain. Okay, it is shifting in the time domain, so it should be multiplied in the frequency domain by a factor e to the power minus 5s. So it is a step function u, so for that we have 1 by s. Okay, so u, if it is a ut, please let me remind you, if it is a ut, so it will be straightforward 1 by s. However, if it is a ut minus some amount, it is delayed or it is shifted in the time domain, that means it is multiplied in the frequency domain. It is just reverse. Okay, just previously what property we have observed, that is this, that means it's property number 6 we have observed till date in the last session, this property. Now when you are dealing with this function, now it is, you see, it is shifted in the time domain. It is shifted in the time domain, that is the property 5. We are now considering property 5. We are focusing more on property 5 now to deal with these waveforms. It is shifted in the time domain, so it must be multiplied in the frequency domain. So that is the exactly that thing we are doing here. So it is a shifted by an amount minus a, so it should be multiplied by a factor e to the power minus as. So that is why it is ut minus 5, its Laplace transform is e to the power minus 5s by s. ut minus 10, it is same thing, e to the power minus 10s by s. So if you take 1 by s common, you will get this is as an answer. So similarly, if you consider f2t, again it is a get function but multiplied with 2 because it's a magnitude 2. So same thing, ut minus 10, so it will be e to the power minus 10s by s. ut minus 15, it is e to the power minus 15s by s. So if you take s common, so outside we have 2 by s, so in the bracket we have e to the power minus 10s minus e to the power minus 15s. So if you consider the third part, that is the third function f3t, so it will be a similar manner. We have got this answer, 3 by s e to the power minus 15s by e to the power minus 20s. Now if you add these three functions to get the total Laplace transform, so you should get 1 by s, this is for f1s, this is for f1s, right? This is for f2s and this is for f3s. So if you add, so you will get, this is the answer. You will get, this is the answer. So it is the Laplace transform of this signal. Staircase like signal, if you apply Laplace transform, you will get this signal. This is as the Laplace transform. Okay. Now proceeding to the next waveform. Now before solving that, let us review one important properties which is called the property of the periodic function. Yes, this property. What is that theorem? Again, if you have a periodic function, with time period t, if you have this kind of waveform, it is repeating after some time interval, it is said periodic function. So if you are asked to evaluate Laplace transform of this entire waveform, so the theorem says you don't have to consider whole theorem at a time. You need to first only calculate the Laplace transform of the first cycle. You need to calculate the Laplace transform of the first cycle, and it will do your work. So once you have done Laplace transform of the first cycle, then you must multiply that result with this term 1 by 1 minus e to the power minus st, where t is the time period of the signal. So that was the theorem for periodic signal. Now we will apply this theorem in this next problem, right? So in this figure we can say that, or we can understand that here time period is 5 seconds. Here time period is 5 second, or maybe in any units of time, and its magnitude is 1. So in the first cycle, if you consider only this much, if you consider only this much, if you consider only this much, then it should be 0.5. So this magnitude is 1 and this x. So slope becomes 1 by 5. So here ft becomes 1 by 5 into t. 1 by 5 into t, or simply t by 5. Okay, because this 1 by 5 is the slope, that is change of y into change of x, and t because it is a ramp function. Okay, now this is actually, if you want to plot this function, so if you have ft is equal to 1 by 5 into t, now if you want to plot this function, it will be go like this, right? It will be something like this. It is going like this forever, but it is not like this, it is actually like this. So the existence of this ramp function will terminate at t is equal to 5. So this can only be achieved if it should be multiplied with a gate function. It should be multiplied with a gate function. Now when we discussed about the gate function, we have mentioned that the property of the gate function is this. So if we just, okay, let me sketch. Suppose this is a gate function, it is 0 to 5, this is magnitude 1. Now if we have a ramp signal something like this, if you have a ramp signal something like this, so if you multiply this ramp signal 1 by 5 into t into by this gate signal, so the result will be like this. Okay, so you must multiply this 1 by 5t with this gate signal to have this shape, right? To have this shape. Otherwise it will continue. You must stop it. So that is why the first cycle, the mathematical representation of first cycle is this: 1 by 5 t e to the power t into e to the power minus 5t. So ft is nothing but t by 5 minus u t minus 5. So ut just is the expression, for ut nothing will change. So if you apply the Laplace transform of the first cycle, now what is the t? What is the Laplace transform of t? So it is 1 by a square. So first term will be by a square. Now what is the Laplace transform of ut? So it will be 1, and since it is shifted by a factor of minus 5, so it will be multiplied by e to the power minus 5s. So that is why the Laplace transform of this function is 0.2 square, 0.2 by a square into 1 minus e to the power minus 5s. Okay, let me repeat. Okay, let me repeat. Let us consider ft is have two part. One part is that 0.2t ut, 0.2t ut, and the second part is 0.2t u t minus 5. As far as this first part is concerned, so 0.2 is constant, so it stays as it is. Now Laplace transform of t is 1 by a square. Now ut, it will not affect much because it is shifted by 0 in the time domain, so it is remains by 0.2 by a square. For the second function 0.2t, the Laplace transform of 0.2t is 0.2 by a square. Now ut minus 5, it means it is time, that means function is shifted by a factor of 5, by a unit of 5 in the time domain. That means from the property 5 we can say that if a function is shifted in the time domain by some unit, it must be multiplied in the frequency domain. So that is why it should be multiplied by a factor of e to the power minus 5s. So the first cycle, if you consider this is only the first cycle. This is only the first cycle. So if you consider only the first cycle, the Laplace transform becomes this. Okay, the Laplace transform becomes this. This is the expression 0.2 by a square divided by 0.2 by a square into 1 minus e to the power minus 5s. Now, according to the periodic theorem of the periodic function, so what will be the total Laplace transform of this total waveform? So you must multiply this with this factor, 1 by 1 minus e to the power minus ts, where t is 5, right? So you can say these two things will cancel out each other. These two things will cancel out each other, and it will be simply 0.2 by a square, 0.2 by a square. So this is the Laplace transform of the entire waveform. Now moving on to the next problem. So we have a similar sort of waveform, but we have 5 to 10 in this limit, or within this time range 5 to 10 we have a 0 magnitude. So now this is for this time period is not 5, now time period is 10 seconds, because for every 10 seconds the cycle is repeated. For every 10 seconds cycle is repeated. So now for this figure 19, this waveform or signal is mentioned in figure 19, time period becomes 1 by 10 second. So similarly, in the similar manner, the function is same. Just like we have evaluated this part, we have evaluated on already this part 0 to 5. So it is 0.2t. Then you must multiply this get function ut minus 5. So there is no meaning to add this 5 to 10 because this magnitude is 0. So anything you write 0 multiplied by that thing is 0. So we are having that. So Laplace transform of the first cycle remains as it is. Now what will be the Laplace transform of the entire waveform? So you must multiply it with the time period, which is 10. Okay. So the Laplace transform of the entire time or the entire cycle is 0.2 by a square that multiplied 1 minus e to the power minus 5s divided by 1 minus e to the power minus 10s. So this expression can be written as 0.2 by a square 1 minus e to the power minus 5s divided by 1 minus e to the power minus 5s 1 plus e to the power minus 5s. Numerator we have 1 minus e to the power minus 5s. In the denominator we have two terms. If you factorize this term, we have first 1 plus e to the power minus 5s. Then we have 1 minus e to the power minus 5s. So these two cancels out each other. So Laplace transform of the entire cycle is this 0.2 by a square 1 plus e to the power minus 5s. So moving on to the next problem, which is given in figure 20, another very standard waveform. So in this figure we have three distinct time zones. We have three distinct time zones, right? The first is, it is 0 to 5 actually. So this is actually 5. So this is 0 to 5. Call this one as F1t. And what is F1t? F1t is already solved many times previously. Secondly, we have time domain or time range from 5 to 15. Time range from 5 to 15, right? Intermediate, this is 10. So 5 to 15, we call this one as F2t. We will solve F2t in a moment. And lastly, we have F3t from 15 to 20. From 15 to 20. So we call this as F3t. So these three parts, if you add these three parts, we will get the total expression or total waveform, right? So let us not discuss any further on that first part, that is F1t. It is solved many times. So F1t is solved many times. So this is actually already done. So I am skipping that. Now for the second part, you see that first what will be the equation. Now that equation of this F2t will become, the equation of this F22 will become minus 0.2t, 2 minus 0.2t. Now you must multiply this with this get function in order to restrict that function or this slope, restrict this slope within 5 to 15. Otherwise it will violate both the limits. Okay, so to understand this waveform or the second part of the waveform run from 5 to 15 seconds, so you must multiply this with that appropriate get function. which is u t minus 5 minus u t minus 15. So if you solve Laplace transform of 2 is 2 by s, and Laplace transform of 0.2 t is 0.2 by s square, and then we have this gate function. Both the gate function is shifted in the time domain, so accordingly it must be multiplied in the frequency domain, e to the power minus 5s minus e to the power minus 15s. So that is the result actually. Is the result. So there will be 4 terms altogether. Third part again. Third part again, it is f3t. So its equation of this line becomes, the equation of this line becomes 0.2t minus 4, and you need to add an appropriate gate function to restrict. So it should be u t minus 15 minus u t minus 20. With that, f3s will be, now when it is 0.2t, it will become 0.2 by s square, and when it becomes minus 4, so it will become 4 by s. So now it is, you see, shifted in the time domain, u t minus 15, so it must be multiplied in the frequency domain by a factor e to the power minus 15s, and similarly for this e to the power minus 20s, you must multiply. So this is actually f2s, f3s and f1s. So f1s is solved, f2s is here, and f3s is also here. So if you add these three, you will get the total Laplace transform of this entire waveform. So these three shaded expressions by yellow, green and sky represents the individual part of this function. So when you add these three, so this becomes f1s, this becomes this entire this thing, this entire this thing, actually it becomes f2s. Lastly, we have entered this thing as f3s. So if you add and if you solve or simplify, you should get the Laplace transform is equal to, represent, it is the Laplace transform of this waveform is represented by this function. So this is the Laplace transform of the entire waveform. the whole waveform. So with this we have discussed the Laplace transform technique applied on few signals, okay, and we have seen how to solve different signals. To recap briefly, we must remember few basic rules. If in time domain, if you observe anything shifted, then you must keep this in mind when you apply Laplace transform. It must be multiplied in that frequency domain. That is rule number 1. Rule number 2 is that in Laplace domain, if you observe anything is shifted, then it must be multiplied in the time domain. Okay, so time domain multiplication means frequency domain shifting, and time domain shifting means frequency domain multiplication. Rule number 3, you must remember initial value theorem and final value theorem, that is utilized to evaluate the function value during transient state and steady state. Transient state means t is equal to 0 and steady state means t is equal to infinity. And other rules are also there, differentiation rule, integration rule, which is the direct application of the electrical network analysis, that is the transient behavior of the series RL circuit, RC circuit or RLC circuit. Okay, so with this I am ending this module. I am ending this session as well as this module. Now from the next module we will see the direct application of the Laplace transform to solve the network problems, which we have already solved using one method, that is differential equation approach. Now we will also solve the same problems using some different technique, which is of course Laplace transform technique, and then we shall compare, means which method or which process is better in what sense and so on. Okay, so with this I am ending this part here. Okay, thank you.